Hello everybody, I'm Geek here. Unfortunately, we had an audio problem at the beginning of this talk, so audio does not actually start until about the 6-minute mark. Sorry for the inconvenience.
with the Windows system loader, so it doesn't necessarily even have to be utilized by the reflective DLL injection. So you don't have to load it that way if you don't want to, because as many of us in pen testing knows, it's all about having options. We need to be able to have options that allow us to be flexible so that we can very quickly and rapidly adjust to situations as they change. So we just want to maximize our options here. All right, so how does this actually work? So I kind of briefly mentioned this, but what we're going to end up doing is we're going to end up undoing the process of the modifications that get applied to the PE file that allow it to exist in memory and to be executable. So we're going to undo everything that ends up getting done. We do all the steps that the reflective DLL injection does in reverse with a single added step, or the Windows loader. So from the perspective of the unloader, it doesn't matter if the PE file that exists in memory was reflectively injected or if it was loaded through the system loader, because we don't want to be dependent on the reflective DLL injection. So all three of these techniques are all completely usable independently, and you can do that, and they were written in such a way when I talk about how the code's been released later, but it's kind of hard to think of a situation where you would want to utilize one without at least another one of them. Like at least two of the three techniques coming together start to end up making it really powerful. And if you put all three together, you're going to have a really good, a lot of options available to you. So what we end up doing is we start analyzing the original PE file, or the PE header that exists in memory, and we're going to recalculate the size of what the PE file would have looked on disk. We then reallocate that much amount of memory so that we can have it all there, and then we start to copy the segments out in reverse as they would have been copied from the PE image and placed into memory through allocations. We're going to go find all of those allocations and we're going to copy them back into this region of memory that we had. Once those are all done, we're going to go through and we're going to undo all of the relocations. So there's a relocation table that's available in PE files that have been loaded. Luckily, this data stays in memory. Windows doesn't like overwrite it or anything like that, so it's going to exist. Finally, after that, we're going to undo all of the imports, and then the last thing, which is a special step, that is the one step that is added and necessary to do in addition to like the unloader and the reflective DLL injection, is we're actually going to talk about a new section that has to be implemented to get a true byte-for-byte copy, and that is restoring a backup from a new .restore section in the PE file. So I've been using PE Bear. I highly recommend it to do a lot of this research. This tool is fantastic. What we actually have right here is in this just like kind of default view, we have the reflective unloader DLL is being analyzed, and right on down here in the bottom, we have on the left-hand side, we have how the PE file exists on disk, and over here in the virtual, we have how it exists in memory. So we can see that these regions are much larger when they're on disk, and that's just because of how it breaks it out when it is in memory. You can see the text section is still the largest. Those are the same size for scale, but what we notice is we have these gaps, those kind of like gray lines in there, and that's just how those different sections get mapped as they get loaded up into memory. So the conversion from how it exists on disk into memory is what is handled by either the system loader, the load library that Windows provides, or the reflective DLL injection. It's going to take care of all of this for us. So we have two options for going from the raw on disk into the virtual, and now what we want to do is we want to be able to undo that and go from the virtual back to the raw. Okay, so the writable sections are the enemy in this case. The reason why is because this is where any kind of like global variables are going to be stored. Even if you don't utilize global variables, if you're writing a C implant, you're probably using the Visual C runtime. Visual C runtime is going to have global variables. So even if you don't write any in your code, they probably exist unless you're for some reason not using the runtime itself and you're doing a lot of like really in-depth stuff and repeating a lot of things, which you're free to do. But what we wanted was the ability to write a normal DLL and not really have to worry about the intrinsics of getting it unloaded eventually. So in order for this technique to work, what we end up doing is we analyze the PE file after it has been compiled. So before it gets injected, because we know that we want this to be unloadable, we run a patch script, a PE patch, which has been released, that is going to analyze the PE file, and it's going to go through each of the sections. It's going to find the sections that are marked as writable, and we're going to back those copies. We're going to back up copies of those into the .restore section, and that .restore section is going to be marked as read only. Now, because nothing in the actual code refers to this .restore section except for the unloader itself, that copy is going to be able to remain in memory unmodified. And what that allows us to do is the normal C program can do whatever it needs to. It can utilize the .data section. It can change all of the different things it needs to in the writable memory. It doesn't need to worry about any of that, but when it comes time to unload itself, we're going to copy those changes into the PE file that would exist on disk, but that's going to give us a corrupt copy. It's not going to be a true byte-for-byte match. So that's when the very last step is we're going to find this .restore section if it exists, and we're going to overwrite the corrupted changes that have been made from the PE file actually running and being utilized. So we're going to restore that copy right on over, and that's what allows us to get a true byte-for-byte copy. Now, the unloader is written in such a way that you could unload any PE file that it's in memory. You just have to pass it a handle. This last step of doing the .restore section is optional. It checks to see if a .restore section exists, and if it does, it handles it as appropriate. But if you wanted to, for whatever reason, unload a PE file that doesn't exist on disk, which you're basically looking at malware at this point, because you can't delete a file that is loaded up, an executable file that's loaded up into memory. That's why if you ever run an executable on Windows and you go and you try to delete it, you can't delete it while it's running. It just doesn't work, and that's because Windows is referencing that copy. So, but if you wanted to, if you had some kind of a section, the only example I could think of would be like malware, if it had done this type of thing and you needed to dump it out onto disk. So you can do that. So a couple of advantages to dealing with it this way. The first one, like I had already mentioned, the original implant or the original code doesn't have to be aware of the fact that it's going to be unloaded. You can basically drop this in and compile it. It can utilize its writable sections. You can have all of your global variables if you need to. There's no problem. Those remain marked as writable, so when the section or when the PE loader adds those into memory and maps those out for you, it's still going to have the proper permissions. You're not going to have any issues with that. The .restore section also only backs up the copies of the writable section. So we don't want to double the size of our binary by keeping a backup of the entire thing, because that's unnecessary. It leads to too large of a size. Once again, downloading that and traversing that across the security boundaries is probably going to be a bad idea. So we want to keep it as small as possible, so we only back up what is necessary, and those are the writable sections. There is a section that is marked as, I believe there's a flag called disposable that gets marked on user mode PE files sometimes, and it basically says to the loader that section that once it is loaded up can actually be released and gotten rid of. Apparently that's an older flag that is utilized primarily by kernel drivers, so the PE patch script also just clears that flag out. It shouldn't be utilized according to Microsoft's documentation, but I can't think of why it would be set on a user mode PE file, so we just clear it anyways just to be on the safe side. But we're going to take care of those two things. It's primarily the writable section. So with that, let's go into demo number 1, and we're going to unload this PE file right here. Okay, so we have this reflective unloader.x64 right here. I have a file hashes extension, so we're going to pull out the SHA-1 of this one right here and do a copy. Now what we're going to do is going to run calc. We're going to pick on calc because nobody likes calc. Nobody likes math. All right, 4352. So we're going to utilize the reflective injector, just the standard stock one that came with the reflective DLL injection application, just the one right off the shelf from GitHub. I already have it compiled. Inject 64. 2. All right. So we just injected our unloader up into calculator. We have this waiting, select OK to proceed window. You can see that it's actually attached to the calc process. So we took our PE file and we reflectively loaded it up into calculator. So calculator is now infected with this image. Now, because it was reflectively loaded, it's not actually tied on memory, so we can delete this. My system freeze? No. And Explorer crashed on me. I have. I've not seen that happen before. I was only infecting calc. And now everything's responding. Okay, so we're going to rewind. We're just going to run that through one more time. Calc. Okay, so calc is down here at 10:32. Explorer didn't restart, so it's all good. All right, so we just did that again. We have that window right there. What we're going to do, though, is we're going to show that it's reflectively loaded, and we're just going to delete the original on disk. Now, I still have that hash in my clipboard. Now, when we select OK to proceed, that's purely there to give me time to go and delete that file out. And as you can see, it got dumped back out onto disk. That's just what this proof of concept does. It reconstructs itself, writes itself back out onto disk. And so now, what we're going to do is to prove that we have the exact original copy again, is we're going to compare the hashes. And if we delete that out and Control V, the SHA ones are the exact same. So that got put up into memory, we deleted it, we brought it back out of memory and dropped it back onto disk, which would be what we would be doing if we wanted to do like persistence through like COM hijacking or something along those lines. If you wanted to rename it, put it into another location, of course that's all arbitrary. This is strictly just a proof concept to show that. But we did not have to have it exist on disk, and we were able to get the exact same one out. All right. So in order to utilize this, this is all public now. At that, you actually can't read that at all. That is way too light against the white. But it's on GitHub under zerosteiner/reflective-polymorphism. It's all right there. So the core API that allows all of this to function is just two simple functions. You have the unloader, which is going to allocate that PE region for you to write it out to. It's going to do all of the unloading for you. And then you have another one to clean up after yourself and to go ahead and free it. I've tested it on 32-bit and 64-bit DLLs and executables. I don't really know... I originally did not really know why you'd want to do it on an executable, because an executable is going to not be able to be reflectively loaded, so you wouldn't be able to delete it off of memory until we combine it with the second half of this talk, which is brand new research. So one final thing, it's all fully documented in the README. All of the code is documented actually in the code. If you go ahead and like download the C code, like all the parameters and everything like that are all documented all up into there, as well as the demonstration shown is in the releases. So let's move on to the brand new stuff, because this is the cool part. Okay, so we now have the ability to have a DLL file that's been reflectively loaded and it's running up in memory, and we can unload it into memory, we can write it out to disk, or we can re-inject into another process if we want to. We have all of these options. But what we were finding at work is that we were getting in these situations where, maybe we want to drop an executable and get that into the client. Well, if we reflectively unload that doesn't work out really well when we want to have a second session. We can't inject an executable. So now what we want is we want the ability to take that executable that's in memory, and we want to patch that and update it into a DLL so we can transform it and then inject that into another process. And from that point, it doesn't matter if the original implant is a DLL or an executable. We can unload it. We can transform it into whatever format we want. If we want to infect another process, it's going to be a DLL. If we want to drop it onto disk for persistence, it's going to be an executable. So this opens up a lot more doors for persistence. We can sort of have it do like automated detection of like what is the best approach right now. If you have like a super cool COM hijacking attack, if anyone's done COM hijacking, you know that you have to have a DLL. Well, if your original implant was an EXE, we don't want to have to go back to like ground zero and have to like retransfer up a DLL. That defeats the whole point of all of this. We only want to traverse one PE file across the security boundary ideally. So we're going to do with what we have. Okay, like I mentioned, adaptation is key. We really want to be able to adapt to our scenario. Something else that I wanted to point out was Both of these techniques, they don't require any kind of I/O. Obviously, I mentioned that you don't have to traverse anything across the network. There's no reading from registries. There is no reading or writing to files unless you explicitly want to dump it out to a file. It's not really necessary as part of the technique. So it's going to be very difficult to determine because it's basically the program is just running analysis and reconstructing itself all within its own address space and everything along those lines. So it'd be kind of difficult to detect because we're not even using like those really janky, easily caught debugging APIs like create remote thread, write process memory, stuff like that. Those types of like traditional techniques that are really going to get you caught. We're not using those because we're all within our own process, so we can make all the modifications that we want. All right, so once we have a PE file in memory and it is unloaded, it's either going to be existing as an executable or a DLL. If we're writing this, though, we kind of have to figure out, like, hey, what are we to begin with? We need to know what our current state is, and then we are going to be able to know, like, okay, are we compatible with what we want to do? In which case, we can skip the transformer. That's no problem. But if we are not, then we need to transform ourselves. So we're going to do this by modifying the analyzing the DOS and NT headers, which contain the different flags to identify whether you're a DLL or an executable. Strictly speaking, you can like call load library on an executable. It starts to get into like some real intrinsics, and like another goal of this project is to ensure that the DLLs and the executables have all the flags set in such a way that it doesn't stand out to someone that's used to looking at executables. We want to make sure that everything's configured as close to like the defaults in Visual Studio, that if you just went into Visual Studio and you did like hello world and compiled it, we don't want to be like setting like, custom base relocation addresses, because we could just set one. We could pick an arbitrary number and be like, everything is going to utilize this base address, and like that'd be fine. But if you're a malware analysis, you're probably going to be like, that's not appropriate. That's not the appropriate value for what I would expect for this file type, and that's going to send up a red flag. Because who would do that? Who would change that value unless you really had a good reason to? So what we end up doing is we end up changing a couple of the fields in the headers as appropriate, and then the harder part, because like that's easy sauce. The harder part is having the entry points. We need to have two separate entry points. We need to have an executable entry point as well as DLL entry point. It's because the DLL entry point needs to actually initialize the Visual C runtime, because once again, like I don't want to force the implant writer that's using this to like get away from the Visual C runtime, because like there's so much stuff in there that like who wants to like really get away from all of that. So that has to do a little bit more than the executable does. I ended up going with XE-main just because that kind of makes sense, because if you've ever written a DLL before, you know that the entry point for a DLL is DLL main, so it just kind of makes logical sense. So what we're going to end up doing is writing both of these entry points, and they're basically just stubs. They're going to do the bare minimum, and they're both going to normalize to a real entry point that's actually going to run your logic that's going to contain your implant. But both of those need to exist, and so that way when we do our transformation, we have those available to us, and we can set the entry point and update it as appropriate given our destination file type. Okay, so the header fields, the image NT contains the actual PE headers. If you've actually like loaded up a executable image, like a normal one on disk. We're not talking like malware or anything like that, but anything from Microsoft, that original like couple of bytes is not the PE header. That's the MZ header, and a little bit after that's going to be the actual PE header. So we have a characteristics field where there is a flag image file DLL. We're going to set that. If we're a DLL, we're going to clear that. If we're an executable, another one is the image file executable image. We're always going to set this because this one's going to be set for both executables and DLLs. So something I didn't quite know about before I started this research is that I knew executables, DLLs, and drivers or .sys files are all PE images. Turns out there's also other PE images that just basically utilize the loader and may not necessarily even have like executable code. I believe these are also the case for like font files and stuff like that. So trying to be a little bit forward thinking, if we ever want to have like a non-executable image and transform that somehow, just want to be able to set that image file executable flag. But like I said, it's probably already set for executables and DLLs. Then finally, the image base. You could go up into Visual Studio and select your own static image base and just like leave it right there. But the image base defaults are different for 32-bit and 64-bit executables and DLL. So you have like 4 separate values. Now, we're not able to transform between 32-bit and 64-bit because we'd have to have like 2 wholly different sets of the code base. But at least between an executable and a DLL, that image base value is going to have different values that are well documented by Microsoft, and pretty much every executable that I've ever looked at, they just utilize that standard image base. And so this is what we want to make sure we update it as appropriate, so we're not standing out when Joe malware researcher tries to open it up and take a look at it. Finally, and most importantly, it's going to be the address of that entry point. So this is going to be an RVA to where it would exist in the PE file. This is not the virtual address of where it exists as it's loaded up into memory, which leads us to a couple of problems. How do we get that RVA? Well, we want to be able to set it to whatever value we want, because once again, we really want to be flexible. So we have two options for effectively getting entry point. First of all, I opted to take an approach where the XE main and the DLL main are both exported. So they're actually included in the exports of it. I figured if somebody goes ahead and looks at the PE file and they see XE main and DLL main, that's probably not as sketchy as like some of the other things. But if you want to go ahead and change those or not import those, you have other options as I will outline. The first option is you could actually utilize the git proc address and git module handle. But the issue with this is that using those two functions, they have two limitations. Number one, it's going to be the address of where it is loaded in memory. And like I just said, the address in the PE file needs to be the RVA, not the actual virtual address of where it's loaded. So we could convert that. We have all the information available to us by going ahead and like analyzing the section headers. So that wouldn't really be a problem. That would be a pretty quick and easy way to do it. But what I didn't like about this approach is that if we relied upon this, we would only be able to transform PE files that also had a loaded copy in memory. I wanted to be able to potentially take a PE file as it exists on disk, not run it through the system loader, copy it into memory, run the transformation, and dump it out. And if it's just copied up into memory and it doesn't have the and it's not actually loaded, git proc address won't work. It's not meant to analyze unloaded PE files, which is what led us to actually writing our own. So, but the DLL main, when you're writing a DLL main, you get called a few times. There's 4 different options that the system loader will call it. You have process attach when you're being loaded up into the process originally, process detach, which just gets called when the process is gracefully exiting, keyword gracefully. If somebody goes ahead and kills it, or there's like a segmentation or fault like that, you're not going to have that opportunity to unload yourself and set up persistence or anything. So be aware of that. And then there's thread attach and thread detach. These are available so that the module can take the opportunity to set up any like thread local variables that may need to be set up using like thread local storage or anything. But if you're doing it through reflective DLL injection, you only get the process attach, and there's also another like secret one that reflective DLL injection adds a 5th one to query the H module, which helps you to set up like so you have a legitimate H module handle, which is a pointer to your MZ header as it would exist in loaded memory. So those are all right there. So this is a quick example of a proof of concept that is utilized in the public. So what we have right here is we're defining our DLL main. We're following the standard signature for DLL main. We're taking our instance, our DW reason for like why we're being loaded. This would be that process attach, process detach, or whatnot. And then our LP reserved parameter. So we're exporting this with the DECL spec DLL export, just like we're exporting our main down here. And then both of these are calling the main function, and it's taking a handle to the module. So this is the real main. This is where the good stuff happens. Our proof of concept happens, our implant kicks off or does whatever. So both of these normalize to that. But what's important to know is that when you are utilizing the DLL, you have to initialize the CRT. So that's what we're doing up in here is we're checking to see if the CRT has been initialized. And we're going to check that and do it ourselves. If you had a normal DLL main method, in Visual Studio, if you just define DLL main, that address is not actually the address of the DLL main as it exists in the PE file. Visual Studio does some hot swapping, some bait and switch type with you, and they actually have their own wrapper that initializes the Visual C runtime for you, which is why we have to do it explicitly, because we're straight up patching the address of the entry point in our version. Okay, so like I had mentioned, we have our 2 options. We have our git proc address with git module handle A. Real easy to deal with. We could just run the calculations ourselves, but then we would have the limitation that we could not do them on images that were not actually loaded by either the reflective DLL injection or the system loader. I wanted the ability to do it just like point it at an arbitrary one on disk and copy it from there without ever executing it. So option 2 is what I ended up implementing, and there is a function for this in the exported code, basically a convenience function that will parse out the export address table of an arbitrary module, and it's going to give you not where the function would exist in memory, but it's going to give you the RVA, so you have that and you're just ready to go. So all you have to do is call this function to parse out the export address table, and that's why we export it, so that way we can identify this function. And then we take that RVA and we update the address of the entry point to this RVA, and we have successfully patched our module's entry point. In addition to this, you could, I have seen them, I've seen proof of concepts online that parse out the export address table. There's quite a few different implementations. You can pretty easily find one. There are even ones out there that are intended to work on unloaded PE files, so you can have ones that'll work on 32-bit or 64-bit, regardless of the host architecture. I kind of just left that limitation, and mine only works for the native architecture. So if you're 64-bit, you're only working on 64-bit PE files, 32 for 32, etc. All right, so putting it together. So our API is simply going to take the address point of the new entry point and the blob as it would exist on disk, but it's already going to be in memory. So we can simply combine this with what we had talked about earlier with unloading the PE image and passing that right into this function, and it's going to take care of all of the patching that we need for that. This is going to take the RVA of whatever you want to update the entry point to, which is where that convenience function to parse out the EAT comes in handy. So that's available to you. If you don't want to use this technique because you like really want to be low, slow, and quiet, and you really think it's going to get analyzed, you probably don't want to utilize the DLL main and the XE main because someone's going to say that's pretty fishy. You can use your imagination to do some other types of calculations, I'm sure, to figure out an alternative way to do it and still use the unmodified APIs. Also, side note, if you are going to use this project to do anything and you do anticipate forensic analysis, I highly recommend you rename the .restore section to something a little bit more innocuous. The .restore section is not being utilized, but if you update it in the C code and in the PE patch PY file, you can name it to whatever you want. You could have it be called .spencer or something. Okay, so once we're doing this, we still have no I/O that's taking place. We're not doing any kind of like network traffic. We don't have to like re-download anything. There's nothing being written off from disk, registry entry. So successful. We can do all of this by analyzing what we originally have in memory. Okay, quick notes on usage. Like I mentioned, the x86 and the 64 are only going to work for each other. If you're going to be converting a PE image, you're probably dealing with the same architecture anyways. All right, so sad time. I was not able to get this technique working with executables for some reason. Everything is solid, but the original like Genesis file has to be a DLL. And there's still some intrinsics that I'm working around through there. There's some differences in the .data section relating to this TLG Microsoft CRT provider prov structure that if you try to convert a DLL to an XE through the transformer, everything is fine. You can even take that XE and you can convert it back to a DLL, and you can go on this loop in an infinite loop, and everything's good. But if the original file is an executable, you can convert that to a DLL, but the DLL will crash. So I'm still working through this. This is an area for improvement for me to continue on. But if you want to go ahead and pull this down and start to mess with it, just compile your project as a DLL, and you should be good to go. It'll handle the Visual C runtime for you, and you're not going to have to worry about that. So still working to resolve that constraint. Talking a little bit through that, so this is one of the issues that I actually found. So when I was getting those differences, I ended up diffing the XEs and the DLLs because that'd be a good starting point to figure out why is this technique not working when I'm trying to patch a DLL, or excuse me, an XE into a DLL, but it is working when I'm trying to go from DLL to an XE. And then back and forth again, just the original file has to be a DLL. So I did what any vulnerability researcher would do is I loaded it up into IDA and I ran Dynamics bin diff on it. Is anybody familiar with that? Yeah? So apparently it doesn't work that great. if you're only trying to analyze for differences in the .data section. As we can see right here, it's pulled out all of my functions, and it's saying that they're all the same, and like, that's great, thanks IDA, I know they're all the same, but it doesn't point out any differences in the .data section, which leads me to PEBear. PEBear was kind of the best utility that I could find to analyze the differences in the .data section specifically, because I know all the code is the same. I just needed to analyze the .data. So if anybody has any recommendations on that, go ahead and let me know. This is what we have right here. So we have our DLL, our 64-bit DLL on the left, and our 64-bit EXE on the right. These 40s right here, if you scroll down further into the .data section, there are some even more differences. But at the end of the day, utilizing the DLL is just going to be the way to go. So looking at it, so taking what we had from PEBear, so taking these addresses right here and the RBA, and actually going back into IDA to map them out. So we're returning to IDA, and then this is how IDA had helped me to identify that there was something going on with this structure right here. So if you actually look at it, something I don't like about IDA is that they're telling me that this is a structure, but then like all the addresses are the same. Like I kind of want the offset, 'cause I know there's a field in here that is corrupt that's leading me to have some issues. But this is how I kind of had identified that. So I know people like kind of like working through or talking about how they are working through problems. So moving forward, one of the things that I'm going to end up doing is I'm going to take these addresses, convert them into the virtual addresses, what IDA has over here. So that's different than what we had seen in PEBear, where PEBear is utilizing the raw, the RBA over here. So we can, using IDA, pretty easily convert those. I'm going to end up setting breakpoints, read breakpoints on when this data is being accessed, and then take a look at the code and identify like what is actually running analysis on this and figure out how I can sort of make that happy and continue on. So ideally, whoever is utilizing this can compile the original as an executable or DLL to once again have those options. If you need to start out with an executable for an operation, my recommendation to you right now would be to just compile it as a DLL and utilize the exact same project, convert it onto a DLL, or excuse me, an executable, and now you have both, and they're both going to work. So let's do a demonstration of this. So this is going to be a separate demo. The public demonstration is going to combine both of these together. I'll describe what that will look like in a little bit. So this is not a reflectively loadable DLL. This executable is simply going to dump itself back out onto disk, but it's going to dump both a DLL and an executable back out onto disk. And we're going to use Python this time and the system loader by simply calling ctypes WinDLL load library. Let's make this a bit bigger here. That's about as big as it gets. Thanks, Windows. That's probably worse. Okay, well, anyways, we're simply using Python to quickly wrap a kernel 32, and we're calling load library to load that DLL. And when we do it, let's move this a little bit over here to the side so we can see what happens to the desktop. We run that, we get a number back showing that it got loaded, and we have this brand new, this reflective transformer.x64.exe. So now what we're going to do is we're going to go ahead and we're going to back up both of these so that we can compare them later. k.dll and bk.exe. Now we're going to double click that one. It ran. And we have a reflective transformer DLL back out now. So we're going to take this. We're going to compare this hash, because you have to compare the DLLs to the XEs because they are different, but the point is that they're different in a recoverable way. So we have our BK and our normal one, and we're going to compare these file hashes, and we have the exact same file hash. We have 5C, AC, E3, 0C, so ta-da, the DLLs are the same, and to prove that we can then go back to an executable again, we have this one existing on memory again. We're going to run that one more time. And where did it go? Oh, that's because this is actually already in memory. So we're going to run this one more time. And now we have two EXEs. We have our BK, and we're going to compare this one to the other one. Because once again, the XEs and the DLLs are going to have different checksums, and that is intentional. And there we go. So we have 72 BB23E3. So we went from a DLL to an XE, back to a DLL, and then that DLL made another XE, and the XEs are the same, the DLLs are the same. So we could, in theory, continue to do this, and unless some astronomical thing causes a bit to get flipped, we'll be all good, and we can just keep going on this in an endless cycle. So, like I mentioned, the public version is going to have a slightly different demo. We're going to have a single DLL that will be reflectively loaded, and it's going to bump the two in together. It's going to have that like select OK thing, and you'll have the opportunity to delete it off of your desktop. And then when you hit OK, it's not just going to drop the DLL, but it's also going to drop the executable. You would then take both, copy them over to like .bk or whatever, so you can get those hashes and compare them for yourself, so you make sure I'm not crazy. And then you just run one of those again, you'll get them both back out again. So should be good. So that will be the public one. So the core API for the transformer is a little bit more complicated than just like those two. Well, it's not really more complicated. There's a couple more convenience features. So like I had mentioned, you need to be able to identify what you're running as in disk, because this is kind of different, because like you're normally writing a DLL and you're like, well, I'm always going to be a DLL, but if you're utilizing this, that may not be true. So you need to have a starting point and know where you are to figure out where you need to go. So to that end, we have a DOS header as DLL and a DOS header as XE. All of these, yes, all 5 of these simply take the output from the reflective unloader. Likewise, you could just load up the file on disk and copy that into memory, and it's going to be the exact same thing. You just point it to that giant blob, and you're good to go. But we have the ability to check to see if we're a DLL or an executable. These are explicit to hopefully in the future be able to identify additional types. If we wanted to like go into hard mode, we could have like a driver or something, or one of those other PE file types. And then once we know what we are, we can, as appropriate, transform ourselves either into a DLL or an executable with the appropriate functions to transform to DLL, transform to XE. Those are going to take that blob, and they're going to take the new address starting point. So you can get that however you want, but for convenience, I provide the RVA from export name that's going to take that blob, and you can give it like an ASCII name like DLL main, and it's going to find the appropriate value to then pass up into the reflective transformer so that you can do that, and you don't have to worry about parsing it out yourself or anything like that, because it's kind of a pain. This is also all live. It's in the same repository. I apologize for how difficult that is to read. It's not, yeah, it's still that bad to read, but sorry about that. This is all fully documented in the C code. In addition to figuring out that additional constraint of why the original one needs to be an executable, I need to copy the documentation out of the code into like a nice readable markdown file. And there is a public proof of concept under the releases for the reflective unloader. The transformer code is live, but there's not like a built one yet. I'm hoping to have that done in the next couple days. But all of the code that you have seen is all live. It's all public right now, so you can go ahead and check that out. And thanks, everyone. And that is much easier to read. That's the exact same link from everywhere else. So that's it. Does anybody have any questions? I have some pretty sweet challenge coins. Pretty sweet BSides challenge coins. Nope. Okay, then I will actually share a question. Oh.
What was the genesis of this idea? Like, you guys encounter a challenge and you're like, we could overcome it this way? Or?
The genesis of this idea goes back quite a few years, actually. When I first got started messing around with like DLLs and like implants and stuff like that, I had this DLL that you could call like load library on, and it would hook like when the process would exit, and it would copy itself up into another process. So it was like whack-a-mole. It would like pop up like a, haha, I'm in PID 132, and you would like close that process, and now it's in another PID. It was a pretty funny joke, but then one of the guys, and it was only intended to be a joke, but then when one of the guys that I work with saw that, he was like, we need to make this into an implant. So when I started looking into like how you would actually do that in the real world, you don't want that DLL to exist on disk, because that's bad news. And that's where the reflective unloader came into play. So that way we could copy ourselves out of memory and then inject into another process by using the reflective DLL injection. So we started using that. That worked out pretty well. So that way we could clone our implants and not have to copy them over the network again, which is going to be where it's going to be most vulnerable. Nobody wants that. But then we had this problem where, like, sometimes you drop an XE and then the reflective, being able to spawn a new one just wouldn't work, because you can't reflectively DLL inject an executable. So if you started with an executable, that was just like what you had, and like you just couldn't do it. But now we wanted the ability to have more flexibility and have it not matter what the original file was. And that was kind of the evolution of that. Yes.
What were the other PE files besides the font files?
.sys files for the drivers, and I'm not. They're like data files for the. I don't remember. I'm pretty sure font files were like the number one that were the non-executable PE files. Yeah.
So when you're actually caching the PE file, it's in memory the whole time, correct?
Yes.
And then you cache it live while it's in memory. Obviously, that's what happens. So is there any way we could write over other tables than just the
Oh yeah.
say like in Linux, like I don't know if that's what it is. I mainly do Linux the global offset table with the functions. You like actually overwrite that potentially?
Yeah, I mean, if you want to do that for like cooking or whatever, once it's all in your memory and it's marked as writable, you can do whatever you want, because like we're not really infecting another process. This is all kind of operating under the assumption that you started this process. You own everything in this process. There aren't really any limitations. You could hook yourself, or if you're being injected into another one that you are interested in, then yeah, you could update like the global offset table or something along those lines. There's not really any permission constraints on those, because it's all just your process.
So if you were like doing like the NT-get process memory and writing to it, you could change values in the PE and live process potentially?
Well, it all actually just exists just like in the virtual address space. You don't really even need to do that. If you can resolve it with like get module handle, the value returned from get module handle is going to be the address of where that MZ header is. So you don't even need to call another function. You can just do it with memcopy if you wanted. Or what I'm actually doing is just direct like pointer access to do it, passing it to a structure and then just accessing it that way. Yep. Thanks. One of the questions I did get that I thought was really good previously was somebody was asking about the .bss section, I guess specifically, is filled with zeros, and they were asking about if I had considered, instead of copying over like all the zeros, because that would be a lot of data and inefficient, which is something that I wanted to focus on, if I had considered compressing it. The answer is no, because then the unloader would have to have a way to analyze and determine that this section can effectively be compressed, then include the logic to compress it and decompress it, and that decompressing it, that additional logic, I'm guessing, I don't actually have the numbers behind it, but I'm guessing just like including and linking against zlib is probably going to increase the amount of space utilized by more than it would save by compressing like 3,000 zeros or something like that. Should kind of be like counterintuitive. And I really wanted to avoid logic that have to handle sections with special cases, because that adds complexity. That's a bigger opportunity for error, and I kind of just don't want to stay away from that, so we have something that's very reliable. That is all my challenge points. So if you guys have any other questions, I'll be around all day. So thank you very much.
Sorry, I'm Geek here. We had some technical issues.
An old version of jQuery, and they feel like they have to implement it themselves in third-party library. You don't. It's in there. It's just painful. So we wrote an article on how to do it. Kind of cool. The most famous